Hi, my name is Patrick Staples, and I'm presenting with Group 2. Our case study was in Gina's apartment, and our subfocus was on noise and lighting, and I'll be presenting on that part here. Indoor environmental quality can depend on more than just air contamination, but on ancillary features such as noise and lighting. Some recent studies have looked at the link between these features and health. For example, Carrera and others linked airport noise with cardiovascular risk over time. However, in this study, they only measured the average noise dose over time and its link with cardiovascular health. In our study, we had access to noise badges, which measure the noise variation and features of the noise over time. So to this end, we developed a new model that captured features of noise over time, and we'll try to link these to potential health outcomes as well as suggestions for the occupants in Gina's apartment. We can imagine that noise over time would look something like this, where there's natural variation at any time in the amount of noise because of conversation, or cars that are going by, or doing the dishes. There will also perhaps be moments where there's heightened noise. Someone just enters the room, or there's construction nearby, or you are watching a movie. And finally, we might also be interested in the total amount of noise that there is. No matter how you contextualize things or what the variation is like, the sheer amount of noise that's available might adversely affect health. Again, most studies only pay attention to the average noise dose over time, but with the noise badges we had more information available to us than that. We were able to capture the features of the total amount of noise, the variation, as well as pre-specified periods where the noise might be higher or lower than expected. And depending on the context, we might want to weight our importance on these even more, or ignore them because the occupants were expecting that noise, or they were the cause of the noise. So we developed a new model rather than just capturing the average for the occupants in Gina's apartment. We captured a few features. Here, y I of t is equal to the noise in decibels over time for scenario I. Now I'll describe the two scenarios that we measured noise for in a second. The mu I is the usual measurement of noise dose, or the total amount of noise on average that the occupants are experiencing. However, we will also add these pre-specified design events, xi of t beta I. Xi specify particular time points where we expect the noise to be higher, or that we capture noise to be particularly high or low in that moment. And beta is going to be the average noise dose at that time. Fi of t is going to measure the across time variation that we will choose to ignore. For example, in this data, there's a natural sinusoidal shape that's taking place that we're going to entirely ignore. That is, we don't believe that this sort of small variation over time is going to make an effect, unless it is a design event. And then the last term here is the amount of variation that is occurring at even very small time points. This epsilon I of t will be reduced to just one measure, which will be the standard deviation of the noise over time. In our data set, or in our situation, we measured two different scenarios where the occupants in Gina's apartment had the windows open, and a situation where they had the windows closed. This is because the occupants might choose to naturally ventilate their apartment or mechanically ventilate it through their HVAC system. We wanted to understand if there was a trade-off between the noise dose that they would receive to the air quality. So scenario 1 is with the windows open, and we measured this for 4 hours because it is winter and it is cold, and these measurements were taken in the evening. The second scenario, with the windows closed, we were able to measure that for 24 hours. Let's take a look at the data. For scenario 1, starting at 7 o'clock, the noise is close to 60 decibels, between 60 and 70. That corresponds to noise a little bit louder than this presentation. There were also 2 of these design events that we noticed around 7:30 to 8:15, as well as a burst near 9:30. We were able to ask Gina afterwards what these were, and we believe that they are construction that's happening nearby. There's a lot of cars in the area and a lot of urban industry. We expect that these sorts of events are to be expected, and that having the windows open will keep the occupants at risk of hearing those sorts of events. These volumes are also pretty high. They're between 85 and 90. To put that into context, a basketball stadium gets at a maximum about 100 decibels high, which was even sometimes the case for our data. The red curve here shows the natural variation that we ignored, and the green curve here, the green line, shows the standard deviation that we measured. With the windows closed, we see a completely different story. This axis has remained the same, and we see that overall the noise has decreased quite a bit. We also haven't measured any design points along here, even though the time that we measured corresponds to the same stretch of time that the construction happened, which was in the evening. We also note that the variation has decreased. So this, just by looking at the picture, intuitively would have us believe that it is better in all cases to have the apartment be mechanically ventilated and keep the windows closed. Let's take a look to see at the parameters or the estimates of our model and what they say. For scenario 1, with the windows open, we see that the average noise was 63.1. The city of Boston allows for mixed residential industrial areas to have an average noise dose of 65. So this noise is fine. However, in scenario 2, the average noise dose is decreased by about 6 decibels. According to Carrera and others, that should correspond to a 0 to 4% decrease in their cardiovascular risk by keeping the windows down over a lifetime. That might be a considerable gain that Gina should consider. We also note that for these 2 design events, that is the construction events, that the noise got up to 85 to 90, which is far above what the city of Boston allows for mixed industrial residential areas. In scenario 2, we don't see any of these design events. So whatever risk these pose, Gina will not be susceptible to them, according to our data set, if her windows are closed. Finally, we note that the variation is 5.3, measured as standard deviation in decibels, for the windows open, and 1.2 when the windows are closed. So there's a 4-fold reduction in the variation of noise when the windows are closed. To our knowledge, there's no studies that capture the effect of the variation of noise on health, but we suspect that it will make a significant impact on the occupants in Gina's apartment. So in conclusion, Stanfield and others have corroborated the effect of Carrera and others that a reduction in overall noise dose is going to increase or decrease the occupant's risk in cardiovascular disease and other health benefits. So we would recommend on the noise dose alone that Gina keep the windows closed as often as possible. However, because of these design events or construction events, and the variation in noise, we have even more reasons to conclude that natural variation, or natural ventilation, if preferred, should be seriously considered against the potential for more adverse health effects by having the windows open. We would recommend that Gina be careful when considering her options for ventilation strategies.